Here's something that might completely transform how we create materials at the molecular level. And it's happening right now in laboratories around the world. Imagine having access to an infinite box of molecular Lego blocks, where you could snap together any combination to build exactly the material you need. Want something that captures carbon dioxide more efficiently? Build it. Need a better battery material? Design it from scratch. This isn't science fiction anymore. It's becoming reality through a groundbreaking fusion of quantum computing and advanced materials science. But here's where it gets fascinating and slightly controversial. Researchers have just cracked one of the most complex puzzles in materials science using quantum computers, and the implications are staggering. Professor Jihan Kim's team at the Department of Chemical and Biomolecular Engineering has achieved something unprecedented. They've successfully harnessed quantum computing power to design multivariate porous materials, MTV, essentially creating a molecular construction kit that could revolutionize everything from clean energy to environmental cleanup. Let's break this down in simple terms. Think of NTV materials as sophisticated molecular scaffolding systems. These structures are built by combining different organic connector pieces, called ligands or linkers, with metal cluster building blocks, kind of like connecting different types of Lego pieces to create incredibly intricate architectural frameworks. The magic lies in their versatility. By changing which pieces you use and how you arrange them, you can create materials with completely different properties and capabilities. These aren't just laboratory curiosities. Either. MTV materials have real-world superpowers. They can selectively grab specific gases from the air. Imagine materials that only capture CO2 while ignoring everything else. Act as incredibly precise sensors, serve as highly efficient catalysts for chemical reactions, and even function as next-generation energy storage systems. In essence, they're like molecular Swiss Army knives. Versatile tools that can be customized for almost any application you can imagine. But here's where the story gets really interesting, and this is the part most people miss. The traditional approach to designing these materials has been like trying to solve a Rubik's Cube while blindfolded. As you add more types of building blocks to your molecular toolkit, the number of possible combinations doesn't just increase, it explodes exponentially. We're talking about millions, potentially billions of different structural arrangements. Classical computers, powerful as they are, would need to examine each possibility one by one, which could take longer than the age of the universe to complete. This is where quantum computing enters the picture as a complete game changer. The research team developed an ingenious solution. They transformed the complex three-dimensional porous structures into network maps, essentially creating a molecular GPS system. Each connection point and building block type gets converted into quantum bits, qubits, that quantum computers can manipulate. Then they posed a deceptively simple question to the quantum computer. Given all these molecular building blocks, which arrangement creates the most stable and functional structure? Here's where quantum computing shows its true power, and this might challenge everything you thought you knew about computational limitations. While classical computers process information sequentially, checking one possibility, then the next, quantum computers can explore multiple possibilities simultaneously. It's like having millions of parallel universes where different molecular arrangements are being tested all at once, and then selecting the best result from across all those realities. To put this in perspective, imagine you're trying to find the strongest house design using traditional Lego blocks. A classical computer would build one house, test its strength, tear it down, build another slightly different house, test that one, and so on, potentially for millions of iterations. A quantum computer, on the other hand, can simultaneously construct and evaluate millions of different house designs in parallel, quickly identifying the optimal configuration with dramatically fewer resources. The team didn't just theorize about this approach, they put it to the test. They ran experiments on 4 different MTV structures that had been previously created and studied in laboratories. The results were remarkable. The predictions from their quantum computing simulations matched perfectly with the outcomes from IBM's actual quantum computers, proving that their method actually works in the real world, not just in theoretical models. And this is where things get controversial. Some critics argue that quantum computing is still mostly hype, that we're years away from practical applications that outperform classical methods. Others worry that we're moving too fast without fully understanding the implications. But this research represents one of the first concrete examples of quantum computing solving a real-world problem that classical computers struggle with. It's not just a proof of concept. It's a working solution to a genuine scientific challenge. The team isn't stopping here either. Their future plans involve integrating machine learning algorithms with their quantum approach, creating a comprehensive platform that doesn't just consider structural stability, but also factors in practical considerations, like how easy the material would be to actually synthesize in a laboratory, how well it would perform in gas absorption applications, and what its electrochemical properties might be. Professor Kim emphasized the groundbreaking nature of this achievement. This represents the first successful application of quantum computing to overcome the fundamental bottleneck in complex multivariate porous material design. He envisions widespread applications across industries where precise molecular composition is crucial, from carbon capture technologies that could help address climate change, to selective catalytic systems that could make chemical manufacturing more efficient and environmentally friendly, to advanced ion-conducting materials for next-generation batteries and fuel cells. The research involved PhD candidates Sinyoung Kang and Younghoon Kim as co-first authors, and their findings were published in the prestigious international journal ACS Central Science on August 22. The work received support from South Korea's Ministry of Science and ICT through both the Mid-Career Researcher Support Program and the Heterogeneous Materials Support Program, indicating significant governmental investment in this emerging field. But here's what I find most intriguing about this development, and where I'd love to hear your perspective. We're potentially witnessing the birth of a new era in materials science, where the bottleneck isn't our imagination or our understanding of chemistry, but simply our computational ability to explore the vast landscape of possibilities. This quantum computing breakthrough might be removing that final barrier. Yet this raises some thought-provoking questions. If we can design materials with unprecedented precision and efficiency, who controls this technology? Will it democratize advanced materials development, or create new forms of technological inequality? Are we prepared for the societal implications of being able to custom design materials for virtually any application? What's your take on this quantum leap in materials science? Do you see this as the beginning of a materials revolution, or are you more skeptical about the practical timeline for these quantum computing applications? And perhaps most importantly, what materials would you want scientists to design first if this technology becomes widely accessible? I'd love to hear whether you're excited about these possibilities or concerned about the pace of change. Share your thoughts. Are you Team Quantum Revolution or Team Let's Proceed with Caution?